Okay, so we're going to continue looking at the Euler totient function today. Remember, okay, this is literally going to be a 1 minute recap of what we said about it up to now. It's a function defined on positive integers, and its definition n is it's the count of the number of integers in the range between 1 and, well, let's say n minus 1, such that everybody's got to remember this. It's what the definition is. It's the count of all the things that are co-prime to it. Okay? Count of all the integers less than n that are co-prime to it. Or really, it's telling you the size. It's telling you the size of the multiplicative group of congruence classes modulo n. Okay. Remember, Zn just on its own. Zn indicates the integers modulo n, so the set of congruence classes modulo n. You'd normally kind of think of as being represented by the standard residues 0 through n minus 1. Forms an additive group, no problem. A nice. You just count away. We're talking about counting as well. So it's a group, no problem under addition. We've got 0 as the identity. Inverses are the negative ones, and so on. But the problem comes when you try and make a multiplicative group out of it. You try and make a multiplicative group out of it. The identity element for multiplication is 1. Okay, 1, or the identity matrix, or the whatever the 1 type object is. Here it's the congruence class of integers congruent to 1 modulo n. That's the identity. But if it's going to be one of these nice algebraic systems of group, then every element has to have an inverse. But we discovered. Okay, this is going into a 2 or 3 minutes summary. We discovered that not all the things in here have inverses with respect to multiplication modulo n. The only ones that did were the ones which were represented by integers co-prime to the modulus. Also, there's Euler's theorem. Why we might be, we're interested in this because it's describing the size of the group of integers modulo n, but it also tells us that if A is in Zn is in the multiplicative group of congruence classes modulo n, then when you raise A to the power phi of n, you get something congruent to 1 modulo n. Okay. So it's knowing the exponent, knowing the value of the Euler totient function allows you to simplify exponents or powers of A. Okay? Because every time there's a factor of phi of n in the exponent, it kind of comes to nothing because it just gives you 1. Okay? So it allows us to simplify exponents. We proved directly last time, we proved Fermat's little theorem, which was the special case of this in the case of a prime number. And that said A to the p minus 1 is congruent to 1 modulo p. We proved that directly, just using our concepts of divisibility and primeness and so on that we've built up to now. And I left as an exercise for you, so I still want you to think about it in addition to your coursework, is to prove Euler's theorem. Prove Euler's theorem using similar techniques. Okay, so if you look at how we prove Fermat's little theorem, very much in the spirit of that, prove Euler's theorem. Okay, we'll return to that. We'll discuss the solution to that in a lecture or two's time. Okay, so that stuff about Euler's theorem and Fermat's little theorem is at the end of chapter 5. What's the central matter in chapter 5? The central matter in chapter 5 is coming up with a better way of being able to evaluate phi of n than its original definition. Coming up with a more meaningful, another way of thinking about it which is more appropriate for number theory. Okay? So there's nothing wrong with this original definition, except it's not telling you much at all about the structure of the function. All right? If I ask you to calculate phi of 10 using this definition, you can simply do it. Inspect every number between 1 and 10, find the ones co-prime to 10, and tell me what the count is. If I ask you what phi of 317 is, same thing. You just look at all the numbers between 1 and 317, which of them are co-prime to 317, etc. So there's no problem with carrying it out. It might take you a long time for a large n, but if you do a load of those things beyond trying to spot a pattern, you're not, it feels quite a naive method. You're not really making use of anything about the number n. And we're not connecting it to other things that we've already studied. Okay? So there is a better way of looking at it. And this is what we call the product formula for phi. So this is the formula presented in Theorem 5.1. Okay, and it's really, really nice. So I introduced this last time. And it's really, really nice because it's based off the prime factorization for an integer. Remember, any integer at all, we can immediately represent it like this, which is a product of prime powers. This is its prime factorization. And this representation of n is essentially unique. You can mess around with the orders of the primes pi around the page if you want, but essentially it's a unique expression for each integer n. And if you have this information about n, you can evaluate phi using the data here, but it's also good, from a conceptual level, that knowing this link between the value of phi and the structure of the argument n helps us to build arguments about the Euler totient function phi. So there's the nice formula is it's the same primes pi raised to almost the same powers. We have to decrease each power by 1. Decrease each power by 1, so that's still looking like a prime factorization, but then we have to throw in some extra factors. For each prime number pi that's featured up here, we have to throw in an extra factor, which is 1 less than pi. So in general, that's going to be a composite number. That will be an even number. For any prime bigger than 2, primes are all odd. So when you look at pi minus 1, it's going to be an even number. So the main guts of chapter 5 is establishing this formula, proving this formula. Okay? And we're going to prove it, essentially we're going to prove it using induction, but not induction as you normally might think of it. So here you've got a formula for a function phi of n. So normally if I say we're going to prove it by induction, you might think, okay, we're going to establish the base case phi of 1. And then prove that if we know phi of k, that phi of k plus 1 is somehow linked to phi of k. But that's not the approach. What we're going to perform induction on here is we're going to essentially do induction on R. So we're going to do induction on the number of distinct prime factors that the argument n has, okay? Essentially. So the base case for this proof will be essentially deciding what the value of the function is when you evaluate it on a single prime or a single prime power. So P is prime. What's phi of P? Okay, we don't have to take a few examples. Well, I mean, we could take a few example primes, but we can just deal with them all once and for all. So if you look at the original definition, how many integers between 1 and P minus 1 are co-prime to the prime P? Co-prime means having a greatest common divisor of 1. If you're asking for a greatest common divisor with P, well, P only has two candidates for common divisors that it can share with other numbers, namely 1 in itself. Okay? Sorry? All of them. Yeah, that's the answer. All of them. Okay? Because if 1 and P are the only two candidate common factors that P can share with anything, well, if you're looking at all the numbers A less than P, none of them can have that factor. So the only common factor is 1. So everything is everything less than P is co-prime. And by everything, I mean starting at 1. Okay? So the value of the Euler totient function on the prime P is P minus 1. Okay, but the real base case of the induction, if I say we're going to perform induction on the complexity of this formula, really, on the number of distinct prime factors that n has, really the base case is to look at what phi of P to some power is. Okay, so that's our next easy case or base case, early cases, I guess would be a better term. That's the next early case. So what's the value of phi when you evaluate it on a power of a single prime? Well, using the original definition, I have to imagine all the numbers 1, 2, 3, 4, 5, etc., all the way up as far as, and the last one is p to the alpha minus 1. I won't bother considering p to the alpha because that's not co-prime to p to the alpha. So you got all these integers here. Expect the power of prime is probably very big, so it's a long list of integers. So which of these are co-prime? Which of these and how many of them are co-prime to P? So those are the ones that are in the multiplicative group of congruence classes, modulo P to the alpha. So some of them are and some of them aren't, or we can turn around the question. We can also ask the question, which are not co-prime? P to the alpha, not co-prime to P to the alpha. That's another way of asking the question. Yeah. Because every integer here either is or isn't. So if we want to count the number that are, we can focus on the ones that are or the ones that are not. Count one set of them, and then we'll know how many are in the other set. Yeah. Well, we can answer this question. I mean, what we're asking for is when is the greatest common divisor of A with P to the alpha? Well, when is it 1 and when is it something larger than 1? Well, what we're asking about is what kind of a common factor can a number share with P to the alpha? And we don't know what the number A is. A can be anything. So let's focus on the P to the alpha. What factors has P to the alpha got to possibly share with other numbers? Just P. Any other factors? 1. Okay, yeah, but that's 1 is shared amongst everything. So, well, P and like P squared and P cubed, and yeah. So the powers of P up to P to the alpha, yeah. But essentially only P really. So the only way you can have a greatest common divisor of A with P to the alpha strictly greater than 1 is when P divides A. If the prime P does not divide A, then the only factors of P to the alpha are P squared, P cubed, a few P's up to P to the alpha. So if P is not a factor of A, then there's going to be no common divisors apart from 1. Okay? So then the GCD will be 1. It's So how many of these integers here have a factor of p in them? Well, somewhere along the list will be p itself. Yeah. So that will not be co-prime to p to the alpha. Somewhere along the list will be 2p. Somewhere along the list will be 3p. You just have to look at all those numbers. Those are all the numbers that are divisible by p. So we need to count the integers in this list. So the first one that is not co-prime to p to the alpha is p. The next one is 2 times p. The next one is 3 times p, 4 times p. What will be the last one? What's the last number there that's not co-prime to? Maybe I'll extend my list up to e to the alpha this time. So if we're looking at all the multiples of p, okay, I know this one is not co-prime to p, but it just fits the. So the last one is this one, you see. Yeah. I look along this list, I keep on counting the ones that are multiples of p. The last multiple of p I'm going to come to is this one. Of course, how should I express p to the alpha in this way? Well, I should express p to the alpha as p to the alpha minus 1 times p. So I'm expressing everything as a multiple of p. So these are the integers in this list that are not co-prime to p to the alpha. And how many of these are there? What's the count of those? Yeah. You just count them. There's 1, 2, 3, 4, p to the alpha minus 1. Yeah. P to the alpha minus 1. That's the number of integers I've written down there. Are there any other ones that are not co-prime to p to the alpha? Are there any other integers hiding up here which are not co-prime to p to the alpha which I haven't listed here? No. Here I've listed everything from this list that has a factor of p in it. Okay. And have I listed them all? Well, yeah, because here I've got every possible product with p times something else, which will be less than or equal to p to the alpha. Okay. P times anything else which isn't on this list will have to be beyond p to the alpha. This is the last one, p times p to the alpha minus 1. That's the last one which gets you less than or equal to p to the alpha. Okay, okay, so those are the ones that aren't co-prime. So the ones that are co-prime should be the difference between the two counts. So the count of the number of integers here is 1, 2, 3, p to the alpha. I'll take 20 the second time. No worries. P to the alpha, and how many are we chucking out? We're chucking out all these ones, which is p to the alpha minus 1. Yeah. So the number of things in the first list minus the number of things in the bad list. Okay. So the things in the good list is the difference. So we normally think of that, and to match it back to the structure of the product formula that we're going for, is we factorize this. So you take out the p to the alpha minus 1, and you see there it's multiplying p minus 1. So that's good. This early case of a single prime, power of a single prime, the value of the Euler totient function is this expression here. So you raise the prime to a power 1 less than it was, and you have this extra factor of 1 less than the prime. That matches the product formula that we're going for, that we're trying to prove. Any questions about that? So it's a nice argument. It's just a quite direct counting argument. We just carefully enumerated the different things there, and we were able to get the right answer. So what kind of thing do we need now to prove the general case? That's what we ask ourselves. Prove the special case. The power of a single prime has the right form as is said by the general product formula. And the general formula says, well, if your original n is a multiple of a number of these different powers of primes, as a general integer will be, then the value of the Euler totient function will be the corresponding multiple of the number of a number of those different terms, each of them of this form here, and one of these terms corresponding to each distinct prime which is appearing in the prime factorization then. Okay, so we got this base case done. So now we need to just expand that up to the general case. What do we need to prove the general case? If we write it like this, it might draw it out a bit more to see what's needed. This is the shape of it. Oops. That's a general integer n here. Okay, some product of powers of primes. That's our phi of n. And we want to say that it's p1 to the alpha 1 minus 1 times p1 minus 1. P2 to the alpha 2 minus 1 times P2 minus 1. All these things multiplied until you get to the end, which is P to the R, alpha to the R minus 1, BR minus 1. So this is just the product formula just written without the capital pi operator. Now I know if it's just phi on one of these, I know if it's just phi on one power of a prime, then I've already proved that. Okay. So the problem is when we've got a load of them multiplied together. So we need to prove that the function phi is multiplicative in some sense. And by multiplicative here, we mean the kind of same thing we mean when we talk about a function being linear, except saying a function is linear, remember, essentially says that phi of a plus b is, sorry, f of a plus b is f of a plus f of b. That's a function being linear, or some people might use the term additive for a function like that. It respects additions. F of an addition is the addition of the x. And if you add in scalar coefficients there that can come outside, then you've got what we call a linear function. Because f of a linear combination is the same linear combination of the x. Okay? So by a function being, but we're not talking about the operation of addition or scalar multiplication here. The operation that's going on everywhere here is multiplication. So we want our function to respect multiples. So we want our phi of a product a times b to be the sensible thing, to be the product of the phi's. Okay? If we could prove that, okay, because that's the structure we see here. We see phi evaluated at a product of things, and the value it's supposed to have is the product of the things that it takes on a single one of the things. Okay. So if we knew that whenever you evaluated phi on a product of numbers, the answer you got was the product of the individual phi values, phi of a times phi of b, then we'd have a proof of that. Okay? So we've already proved it for a case of one factor. And this result allows you to build it up by induction to any number of. And you do know functions that behave like that, or have that kind of structure. It's featuring in your coursework. For instance, the determinant of the product of two matrices, square matrices of the same size, is the product of the determinants. So, it's not a crazy ask for a function to behave like this, because there's the determinant function behaving like it. So it's, it does happen. However, this is asking too much at the moment, okay? Because this isn't true in general. It's too much to hope for in general, okay? If you look at the value of 5, 6, what's 5, 6? How many things between 1 and 6 are co-prime to 6? So there's 1, not 2, not 3, not 4, 5. So it's just 2. And 5, what's 5? 2. Many things between 1 and 2 that are co-prime to 2. There's just 1. But 5, 12. How many things between 1 and 12 are co-prime to 12? 4? Is that what you said? 4. That's quick. You're on the ball. Well done. Is it correct?
1, 5, 7, 9. And 11. That's 5 then.
That's 5. Which one was wrong?
Not 9, but
Not 9.
Oh, not 9.
So you're right, Mark. Good. That's good. Well, what's the problem here? 12 is 2 times 6, you see. So 5, 2 times 6, 5, 12 is not the same as 5, 2 times 5, 6. Okay, so it's too much to hope for that it's multiplicative. But actually, in number theory, the term multiplicative doesn't mean that this property, if this is true for any A and B, in number theory, we would call this completely multiplicative. The term multiplicative means something slightly weaker. And what's the point of these things we're multiplying together? They're not just any old products. They're products of distinct primes. So the key thing about them is they're co-prime to one another. They're kind of completely different from a prime factorization point of view. Power of 2s, power of 5s. There's no overlap between them. There's no common divisor between them. So the property we want is this property, which is called multiplicative in number theory. If you just say multiplicative generally, you mean kind of something like this, something that applies to all products. But if you say it in a number theory context, what we normally mean is as long as it works for co-prime factors. So as long as my A and my B are co-prime to one another. If it works then, if this equation is true then, that's all I need. Okay, because the chunk that I've the chunk that I've already proved the result for is a power of a prime. So if I have my thing written as a product of power of distinct primes, those are all co-prime to one another. So if I know that it's multiplicative in this sense, just on co-prime products, then that will be enough to prove this general formula. So that's what we need. What do we need to prove that phi is multiplicative? We need to show what do we need to show that phi is multiplicative like this? We need to show that if the GCD of A and B is 1 co-prime, then on that product, phi of AB, phi of AB is just the product of the phi's, phi of A times phi of B. And this then is the central proof in chapter 5. It's all laid out in the notes there, but we can talk through the main elements of it here. We need a couple of lemmas. We've already more or less proved all of these. The first thing is if A and B are congruent modulo n, then the GCD that they have with n is the same. Okay, that was a previous exercise that we proved. Two things are congruent modulo n, they have the same common divisor with them. Greatest common divisor. Secondly, there's a thing about breaking breaking GCDs down with respect to products. So when is a U co-prime to a product of V and W? Well, that's true if and only if it's co-prime to both of them. That's a kind of nice result as well. When am I co-prime to a product of two things? When I'm co-prime to both of them individually. And it goes the other way. When I am co-prime to two things separately, then I'm also co-prime to the product. That's easy to see when you think about it as co-prime, meaning you don't share any prime factor, or your prime factorizations are distinct. This thing on the right-hand side is saying the prime factorization of U shares nothing with V, and it also shares nothing with W. But then what is the prime factorization of V times W? It's just whatever the prime factorization of V is stuck onto the end of whatever the prime factorization of W is. So if U shares nothing with V and it shares nothing with W, then it can't share anything with the product of V times W. And it goes both ways. If U shares nothing with the prime factorization of V times W, well, the prime factorization of V is just a part of this, so it can't share anything with the prime factorization of V. And similarly, the prime factorization of W is just a part of the prime factorization of V times W, so U can't share anything. Okay. So those are some preparatory lemmas that we have to do. So I think this brings us to the main central theorem, theorem 5. Lemma 5.5. Presenting these intermediate results, we're calling them lemmas because we're on the way to proving the theorem, which is this product. Any questions about the argument up to now? Okay. So we've got phi. We know that phi behaves as expected on the power of a single prime. We want to show that it has this general behavior, and we've identified now that as long as we can show it's multiplicative co-prime products, then it will have this necessary behavior. Okay, so we can prove lemma 5.5. So this is saying GCD of A and B is 1. This implies that phi of AB is phi of A, phi of B. Now the proof is kind of long. I've put in a good deal of explanation there, and you'll see it's a nice example of something that's mostly just prose. It's not doing calculations as such. It's just laying out the argument and describing the reasoning clearly. But the whole thing basically centers on, we will directly enumerate all the integers, count all the integers in the range 1 to AB that are co-prime to AB. Okay, so we're going to evaluate the left-hand side. Okay, so we're going to look at all the integers between 1 and AB, count the number of ones that are co-prime to AB, and discover that it is obviously or clearly phi of A times phi of B. Okay. We're going to evaluate the left-hand side using the original definition. And the way we're going to do it, it will become clear that the answer is phi of A times phi of B. There's a lot of kind of prose calculation there. I'm just going to summarize it here. And it mainly centers around laying out all the integers in a grid. we're going to lay out, just like before, when we laid out all the integers between 1 and p to the alpha and thought about counting through the list in a systematic way. Here we're going to lay out all the integers between 1 and a times b, but we're going to lay them out in rows of length b. And this is 2b minus 1, 2b. So the last row ends with a times b. And we've got a times b minus 1. And it begins back here with a minus 1 times b plus 1. A minus 1 times b plus 2, etc. Oops. The dividing line there just to clear what the. Okay, so we've laid out all the numbers in a grid, in a matrix, with b columns and how many rows? 1, 2, 3. Well, actually, look, it's the multiple of b that's counting the rows. 0 times b, 1 times b, all the way up as far as a minus 1 times b. So there's a rows. B columns and a rows. Then we're going to stare at those numbers and we're going to count how many of them are co-prime to a times b. Okay, but there's a reason we've laid them out in a rectangular matrix, is that's the way we're going to count. Okay. So first of all, we're going to look down, we're going to consider the columns. How many columns have we got? We've got b columns. If you look down any particular column, what do you notice? What we notice is that all of the numbers are congruent to one another, modulo b. So I've got 3b plus 3, then it'll be 2b plus 3, 3b plus 3, etc., all the way as far as a minus 1 times b plus 3. It's the same in any column. Okay? So within any column, everything is congruent to everything else modulo b. Okay, so sorry, I should have said by the lemma first. Using above lemma, we are looking to count the integers here that are co-prime to a and co-prime to b. So that was the first. That was the second lemma. Something is co-prime to the product a times b if it's co-prime to both a and b. So I'm looking in this grid. I want to count the number of things that are co-prime to a and to b. But then within each column, everything is congruent to each other modulo b. Everything's congruent to 1 modulo b. Everything's congruent to 2 modulo b. So how many numbers here are co-prime to b? Well, the other lemma says that if two things are congruent modulo b, then they have the same greatest common divisor with b. If you look at the column headings, how many of the column headings are co-prime to b? Well, we would call that number 5b. Yeah? How many of these numbers, 1, 2, 3, b minus 1b, how many of those are co-prime to b? The answer is 5b. But if say the 3 is co-prime to b, well, everything here is congruent to 3 modulo b. So everything there is also congruent to b as well. So if the number at the top of the column is co-prime to b, so is all the numbers in that column. And How many number of those column headings are co-prime to B? The answer is 5. So there are 5 B columns, all of whose entries are co-prime to B. Sorry. Remember, we're trying to count the things co-prime to B and to A. So looking first at co-prime to B. 5 B columns that are co-prime to B. And everything that is co-prime to B is located in one of these columns. Everything co-prime to B is in one of these columns. Okay, so we've identified everything that is co-prime to B. Now we have to look which of those numbers are also co-prime to A. So we choose one of these co-prime columns. Let's say it's column 2. You look at all the integers in column 2. Now we're interested in deciding how many of these, okay, we're assuming they're all co-prime to B, how many of these are also co-prime to A? Well, then we have to consider the congruence class of these things modulo A. We notice that within any column, we have A integers. Integer A, that's the number of entries there are in any particular column. E.g., in the second column, you've got 2, B plus 2, 2B plus 2, 3B plus 2, all the way up as far as A minus 1 times B plus 2. These are all congruent to 2 modulo B, but now we're looking at them, we're considering them from an A viewpoint. So there are A integers, 0, 1, 2, 3, up as far as A minus 1. So there's A integers there. When you consider their congruence classes modulo A, we see they are all distinct. We see that they're all distinct. How is that true? E.g., i.e., if you take 2 of these things, so if you take an IB plus 2 and you assume it's congruent to a JB plus 2, that's 2 of these numbers here, assume they're congruent modulo A, that implies that A divides their difference. Now their difference is I minus J times B. The 2's cancel when you take the difference. So if 2 of these were in the same congruence class modulo A, if you assume that would force you to say A divides the difference. But big assumption lying behind A and B in all of this is that A and B are co-prime. So if A divides the product, it can't divide B, so it has to divide this factor, I minus J. So that implies that A divides I minus J. See, where have I and J come from? I and J are 2 of these indexes here, which begin at 0, go 0, 1, 2, 3, 4, all the way up as far as A minus 1. So I and J are between 0 and A minus 1. So how can their difference be a multiple of A? The only way that can happen is if I and J are actually the same. Okay, because we're talking 0, 1, 2, all the way up as far as A minus 1. I and J are somewhere from in here. And saying A divides the difference means that the distance between I and J is a multiple of A. But the furthest apart I and j can get is a distance a minus 1 apart. And that's not a multiple of a. So the only distance between two things that is a multiple of a, if the two things are chopped here, is a distance of 0. The two things are the same. So you can't have two of these things being congruent modulo a. And there's a of them, so that means they represent all the congruence classes modulo a. So within any column, we have a entries. It's difficult to indicate that I mean the integer a here, not the English word a. We have a entries representing all the congruence classes mod a. So within any column, how many things are co-prime to a? We don't know, but we know what name to attach to that number. That's the number phi of a. Okay. Within any column, how many of these things here in column 2 are co-prime to a? Well, I know there's phi of a. So I've got a complete system here of representatives of congruence classes modulo a. So there are phi a things here co-prime to a. So that's basically the argument. There was our grid of numbers between 1 and AB. We were trying to count the number of things co-prime to AB. The lemma told us that you're co-prime to AB if and only if you're co-prime to A and you're co-prime to B. So we counted the number of integers here, co-prime to B and to A. There are some of the columns are co-prime to B. The number of them is phi of B. Within those columns, within each column, some of the entries are co-prime to A. The number of them that there are is phi of A. So the things we're counting are located in some of the columns and some of the rows. So to count the total number of them, you just multiply the number of good columns by the number of good rows. So you get 5b times phi of A. So there are phi of A times phi of B integers here, co-prime to A times B. Okay, so that tells us that phi of AB is equal to phi of A times phi of B. So by induction then, we can say that we proved the product formula. So the phi product formula can be proved by induction. Okay, so there are some remarks in the notes that just kind of finish that off, but we've seen it all. We've seen the base case, which is phi evaluated at the power of a single prime. This multiplicative property of phi is the linking step in the induction. Okay. That allows you to add on an extra co-prime factor. Okay, I've overrun a couple of minutes, I better finish there. We'll reflect on this a bit more in the next lecture.